Hello everyone, my name is Ali and I'm going to talk about instantaneous signal coalition detection where we use in-band full duplex technology. This work has been done with Kyle Leuven and IMEC in Ghent. But first of all, let's have some introduction about the topic. Human basic necessities are changing rapidly. A century ago, food, shelter, clothing, then family safety and education. But today, neither of us can survive without our smart watches and smartphones. That's why today there are thousands of devices connected to wireless networks and internet. It means that they have to share the spectrum fairly and efficiently. Let's have a simulation by NS3 on a Zigbee network. As you see in this graph, when we increase the number of nodes, the number of transmissions also increases exponentially. In other words, within a denser network, there is a higher chance of signal coalition. So let's have a look on the impact of signal coalition on the throughput and energy consumption of a network. So in the graph at the left, you see when we increase the number of nodes by, let's say, 140, the throughput gain decreases 90% comparing with the case that we have 10 nodes. The graph at the right shows the energy consumption performance. So you see, for example, with a network with 80 nodes, the network has to consume 10 times more energy comparing with the network with 2 nodes. And that's why we have to find the solution to resolve the impact of signal coalition. Actually, coalition detection can be implemented on both transmitter and receiver, but in this work our focus is on an approach that does it at the transmitter side. So we see how it works, what is the mechanism, and how much it improves the network performance. So let's compare carrier sense multiple access CSMA in short with coalition avoidance and coalition detection. Suppose we have a node TX1, it checks the channel. If the channel is free, it starts transmission. And think of another node, TX2, which has a packet to be transmitted. So it sends the channel. If this CCA, by any reason, fails to detect the channel correctly, this node also starts transmission. So for sure, in this time, both of the packets are distorted by each other. On the other hand, in CSMA CD or CSMA with coalition detection, one of the nodes can sense the coalition or interference from another node whenever it happens. So then, if it can sense it, it can take an appropriate reaction. For example, it can stop transmission. So this way it saves energy, and at least we make sure that one of the packets is delivered correctly. But two important points. First of all, this transmitter or TX1 has to sense the channel in the transmission time. Second, the detection time, this tiny gap here, should be as short as possible. So we make sure that the second packet is not distorted much. Here are the simulation results showing how much energy we can save and how much throughput gain we can achieve with coalition detection. For example, here at 120 node, with 120 nodes, you see that this amount of energy can be saved with coalition detection. At the right, you see the throughput gain. And for example, here with 120 nodes, so you see the throughput gain is almost doubled. As I mentioned before, in-band full duplex is the key enabling technology for such a functionality. So here you see the communication scenario. We have one self-interference canceller module to provide sufficient isolation between TX and RX. We have a second party transmitter to, let's say it's the interferer, and also a receiver. Actually it is the destination. So this node is going to send a packet to the receiver here. So, but let's see what are the components at the receiver of the device. So this YT is the signal that we receive here in the receiver side. There are two main components that we're going to distinguish. First of all, the residual self-interference after analog cancellation, and the second one is the coalition caused by the second party transmitter. So the task of the coalition detector is to distinguish between these two components and just raise a flag whenever the signal is collided by another device. So we show that with coalition detection, we can improve the throughput performance of the network as well as the energy consumption. But the assumption was to detect coalition in 0 seconds, very fast. So here we review goodness of fit as the state-of-the-art detection technique and introduce our methods which can detect coalition faster than the current state-of-the-art. So here is how goodness of fit method works. So this statistical approach is based on two curves: the cumulative distribution function of the residual self-interference, let's say the learning signal, and the CDF or cumulative distribution function of the signal under test. So basically, after forming these two curves, it measures these two gaps, the maximum distance between the curves when the blue is stronger and here when the red one is stronger. And the Kuiper criteria is the sum of these two values. So whenever this sum is higher than a threshold, we can say the two signals, the learned signal and the signal under test, are two different signals because they have two different cumulative distribution function. So with this kind of approach, what it could achieve is 250 microsecond detection time for a Zigbee-like waveform with 95% accuracy and 5% false alarm rate. The point is, this approach doesn't need much information about the file layer. However, it is a bit complicated in sense of real-time implementation. Although 250 microsecond coalition detection time is impressive by goodness of fit, it doesn't satisfy a wide range of applications like vehicular scenarios. So jointly with IMEC, we decided to start a research to see if we can improve the detection time by a factor of 10 and minimize the false alarm rate simultaneously. The first approach in our research is based on estimating the SNR of the signal. In the case that we don't have a coalition, what we receive is the residual self-interference after analog self-interference cancellation. So we expect a high level of SNR. Whereas where we have a coalition caused by a second party device, the SNR of the signal decreased. So this way we can figure out whether the signal is collided or not. So here is how it's implemented. We have IQ samples at IF, we feed it to time synchronization, frequency synchronization, and we have the cancellation, and then we estimate the SNR. So I'm not going to bother you with the formulas, but here is how we estimate the SNR of each one of these quadrants, and then we average over all of them. Once the SNR is ready, we determine a threshold, and if the SNR is higher than threshold, we can say that the signal is a coalition-free signal. So to define this threshold, we have such a strategy. We run many random tests, and based on those tests, we try to minimize such a criteria, which is actually the detection error. The second technique is motivated by the fact that the interference-free signal creates a different let's say, distribution. So why not we use a neural network and train it with raw data? Somehow it learns how to detect the coalition. Here is how the idea is implemented by TensorFlow. We have a convolutional neural network. The input layer is fed by the raw data, amplitude and phase in this case, and the network doesn't need any prerequisite decoding steps. And then we have convolutional layer 1 and the second convolutional layer, and finally the dense layer, which determines the state of the channel. So to keep this network as simple as possible, we use ReLU activation function, which is quite simple to be implemented on real-time hardwares like FPGA, and we also have softmax activation function and such a logistic cost function at the last layer. They are nonlinear, however we don't use them for the test phase, and they are merely used to train the network. To evaluate the proposed techniques, we use the same measurement setup as in this work. So this measurement setup includes two USRPs, one to play the role of interferer, and another is an in-band full duplex capable STR. So it has a, let's say, electrical balance duplexer to isolate the transmitter and the receiver. So here you see the PCB of the electrical balance duplexer, and the signal at the receiver is 8 times oversampled, and the waveform we used is a Zigbee-like signal. The EBD in this setup can provide 40 to 60 dB isolation. Here is the test results for measured database as well as the simulated database, which is produced by MATLAB. In this case, we had 40 dB isolation between TX and RX, and the detection time is 20 microseconds. The x-axis shows how much the coalition is weaker than the residual self-interference. In this graph, you see that both of the techniques can detect, let's say, 100% of the coalitions, even if the coalition is 30 dB weaker than the residual self-interference. And more importantly, the false alarm rate in all the cases is less than 1%. So we also carried out the same test for the case with 60 dB TX and RX isolation, and you see that the DSK technique can deliver a better coalition detection performance. As a cost, the false alarm rate is roughly 1% worse than the CNN coalition detector. Conclusion: we could achieve 12 times faster coalition detection plus 3 times less false alarm rate comparing with the state-of-the-art goodness of fit coalition detector. For machine learning, there is a chance of overfitting. However, this technique is quite straightforward to be implemented on real-time hardwares like FPGA, and there is no need for pre-decoding steps like frequency and time synchronization. For domain-specific knowledge, setting the threshold is a bit tricky. However, when the isolation between TX and RS is high, this technique can deliver a better, or let's say more accurate, coalition detection. I have one more slide to promote the work. The challenge is still open. Everything has been loaded on IEEE data port, all the data sets and MATLAB and Python codes. So you can try over our codes and data sets and see if you can achieve a better, or let's say faster and more accurate coalition detection. Here are the references, and thank you for listening to my presentation. My email is there if you had any question.